This entire talk has seriously been inspired by a conversation between two professional adults where one person said we came up with some rules that automate a bottleneck, and on the other side of the room there was someone saying, but that's not AI, it's not even data science. And kind of what I want to talk about is that back in the good old days, we had these systems that would do data science, but the way they worked is fundamentally different than what we do nowadays. Before, it was kind of normal that you said, well, we've got some data and we want to automate this decision-making process. So what we then do is we get a domain expert in, and maybe with some probability rules, but effectively we get the domain expert to come up with some rules such that we can automate this decision-making labeling. Like, we can generate labels this way, we can automate decisions. That's how that used to work. Nowadays, it's a lot more fashionable to not do the effort of actually understanding the data and sort of coming up with domain rules. Instead, nowadays, what we do is we just apply a lot of math and geometric tricks to separate data points with this thing called machine learning. We just put it in a big bowl, and eventually rules will come out. Now, there's merit to this idea because it's automatable, and we also tend to get high accuracy scores. But I've started wondering for a while now that in this transition from these rule-based systems down to this more machine learning way of thinking, that maybe we should admit that we didn't get better at solving all of the problems out there. In fact, maybe this machine learning way of thinking is introducing new kinds of problems, and maybe what we should do is figure out a better way to combine the two. That we can say, well, we've got these rule-based systems that the machine learning can use, and we've got this machine learning that the rule-based systems can use. My hypothesis is that if we approach problems this way, odds are that we have better solutions. So the way that I want to talk about this is first I want to talk about some lessons I've learned while making content for the Spacey project on YouTube. Then I would like to also discuss some lessons I've learned in the past half year while working for my new employer, Raza. And then I want to maybe take those lessons and see if we can apply them to scikit-learn, which will then conclude by saying, well, I've made this new package and I think it's going to help solve some problems, especially in this particular space. So let's talk about a very specific problem that you see quite commonly in natural language processing. There's this problem called NER, which stands for Named Entity Recognition. And what it basically boils down to is that when presented with a bit of text, you might want to be able to detect specific entities from it. You can think of like phone numbers, for example, but you can also think of, well, I have these people references that I would like to retrieve. Maybe there's a reference to an organization or to a city or to money. But we would like to have an algorithm that can detect very specific entities for us in an automated way. And what I've been doing in the last year, kind of as a hobby project, the creators of Spacey reached out to me and asked me if I was willing to help them make some good content on YouTube. And I've been solving a variant of this problem. I wasn't interested in detecting people, though. What I thought was interesting is to go out there and get me a data set about programming languages. Because I figured it would be interesting to see if I can make an algorithm that can automatically detect programming languages or programming tools from a text. Because I think there's some interesting applications that you can do with that if you can do that properly. The thing, though, is it's actually quite a hard problem. It's by no means obvious. I mean, sure, it's pretty easy to detect like the string of Python, I suppose, right? I mean, that's relatively easy. Just regex it and you're done. But the problem is you can't always do that because you got this programming language called Go. And the thing with Go is it is a really common word in the English language, but the way it's most often used is not in reference to a programming language. In fact, Go is the most common verb in the English language. So even if you were to throw embeddings at it, odds are you're not going to be hitting the thing you're interested in. So you got to do something maybe more clever. And machine learning algorithms actually have a hard time doing this. So I had to do something else pragmatic. So what I'll do now is I'll just show you the short version of the trick that got me there, but then I'll talk about the larger issue when I'm done talking about syntax. But what I kind of want to do just real quick is just show you how this amazing feature in Spacey works and how it's helped me solve this problem. Here's a Jupyter notebook, and what I'm doing here is I'm loading up a natural language processing model from Spacey, the small English model that's trained on a web corpus to be specific. In short, what Spacey does is you can take that model object, give it a bit of text, and what comes out is a document that contains tokens. And In this particular case, for the English language, it's just a white space, tokenizer. But one of the things that Spacey will do for me is it will add information to all of these separate tokens. There's a machine learning model that's quite general that does that. In particular, what you're going to get is this token. What's the part of speech for it? So you can imagine, well, is it a noun or is it a verb? Werkwoord, bijvoeglijk naamwoord in Dutch. And the thing is, that's kind of nice, is given such a general model for the grammar, it's relatively easy to come up with a rule-based system for the Go programming language. And in Spacey, what you would do is you would say, well, I've got this matcher object, and the matcher basically accepts a pattern definition, which in this case would be, well, if the text is lowercase go and the part of speech of that token is not a verb, okay, then I can match and say that that is indeed the Go programming language. What I can also do is I can add a second pattern saying if it's Golang as text, then it's probably also about the Go programming language. And suddenly when you just come up with this fairly simple rule-based system, it just kind of works. Here we see that I program in Go, Go is detected correctly. I go and write code, well, Go is a verb here, so it's not detecting that as a programming language. How to make web requests in Go? It kind of works. Now, of course, I'm using something machine learning under the hood to make this rule-based system, but I hope that you would agree that this is relatively robust, and I can stand by my own domain knowledge that this will probably work for a lot of cases. And just to give like a slightly better impression of what else you can do with these rules, what you can also do is you can generate these rules automatically. Because in the end, the definition is just a list with a Python dictionary inside of it, what you can also do is write a function such that you can also capture the version of a programming language. If you're doing natural language processing and you're interested in fetching programming languages, I hope that you would agree that Python 2.7 is different than Python 3.6. It would be kind of a bummer if we fetched Python, but not the version number. But the nice thing about this rule-based system is that I don't have to do this endless labeling or collecting tons of data. I can just kind of come up with a rule, and that'll probably go ahead and work. So I hope, if nothing else, that you would agree that this rule-based system, it's not even really machine learning end-to-end anything, but it is really pragmatic. It is super helpful. This, however, was only the introduction. The real lesson comes now. Because you have to imagine, I now have this matcher object, and the matcher object is just quite pragmatic. I can just come up with some domain knowledge, apply that to some CSV files. I can look at some rows, and I can look at the CSV file for a bit, maybe add some more matcher rules. But by doing this, what I got effectively was this data set that I could go ahead to label. What I then did is I took that labeled data set, and then I went ahead to train this actual machine learning model. Spacey comes with some deep learning models for you to use as well. So what I did effectively was first make this matcher ruler, and then get this data set such that I can make a machine learning model, and that I can kind of compare both approaches. I also hope just here you would agree that that's useful, because we would expect this machine learning model to perform much better than the basic rules, so to say. If the basic rules work better, we should not consider this guy. So Spacey makes this quite easy. From the command line, you can basically save your rule-based system as well as your machine learning model, and you can do some comparisons. And one thing that stuck out to me was that, you know, if you look at the F1 score, this is the machine learning model. This is the other one, the rule-based one. And, you know, this is just way higher. And the reason why it's way higher is because the precision is way better on the machine learning side. Now, a bit of a hint. At these moments, you shouldn't go ahead and say, the machine learning model is therefore better. Because there's something really weird happening here, and I'm wondering if you can see it. In the interest of time, I'll just tell you, but isn't it kind of weird that the recall for the machine learning model is lower than the recall for the rule-based system? I might argue that the rule-based system, that's bounded, right? The machine learning model can sort of hopefully look outside of the bounds that I as a human have declared and maybe generalize by covering more ground. But that's not at all what's happening here. Apparently, the precision is higher, not the recall. So then I'm wondering, is this machine learning model even generalizing? So at moments like this, I like to not go for the better model. At moments like this, I like to understand what the difference is. So the way I went about that is by basically saying, well, let's not take the qualitative route. Let's maybe do this a bit more qualitative. So let's not go for quantity. Let's go for quality. That one, sorry. And here are some examples that I found. In instances where they both failed, effectively, a lot of that was contributable to the tokenizer. When you have something like C# and you have C# version 7, or C# immediately a comma and then like a list of programming languages, okay, it's good to understand that the tokenizer that's trained on normal English languages is going to have a bit of trouble here. It's not going to help me, but it is good to understand a failure scenario for this system. Instances where both models tended to work equally were moments where we're talking about Java and Python and Golang and JavaScript. Those were instances, it just got all of them. But there were moments where there was disagreement between both models, and that's where the interesting thing started happening. In particular, the main thing I was surprised by was that the machine learning model was unable to capture Common Lisp. This surprised me because Common Lisp is pretty well defined. You can just get it by string matching. But then after investigating, I found out that Common Lisp doesn't exist in the training data at all. The reason why Common Lisp was detected by the rule-based system was because I was able to write down with my domain knowledge that this programming language actually exists. And this is a nice reminder. A rule-based system can actually make a proper classification even if there's no data. That's the art of it. That's what a rule-based system can do. If there's no examples of something that you're interested in, if there's no examples of the thing that you're interested in, machine learning is not going to help you. But it's weird because you sometimes are able to define what you're interested in, even if you don't have data for it. So this was a clear win for the rule-based system, but there was something else happening as well. The fact that it couldn't detect Go indicated a more subtle problem. And here's the issue. Java, Python, and JavaScript, those are all pretty easy languages to detect, but they're also by far the most frequent languages out there. If I'm not mistaken, I think Java, Python, and JavaScript are the most popular ones out there. So it's no surprise that the Stack Overflow dataset, therefore, has lots of examples of those, and maybe not as many for Go. And if I then start thinking about, oh yeah, but the precision was way higher and the recall was lower, then you can start wondering, well, that dataset that I'm judging this system on, if it only has these easy examples, then I'm judging my grid search maybe on the wrong thing, and there's evidence of that happening now. So I'm super happy I didn't do grid search here, but then now you get to think about how to actually solve this problem. And I really like the system that we ended up with. Back to the drawing board, what I ended up doing is I said, well, let's have a minimum amount of examples per programming language. So, just to make sure that also the more obscure languages, we have at least 50 examples of each in the training data just to start with. And it includes some of the languages that are harder to detect. Next, what I did is I said, well, let's just have a look at when both of these models disagree. And let's then also say that the instances where both of those disagree, that's the moment when I'm going to start labeling again. I'm not just going to grab randomly from the CSV file, because odds are I'm just going to get the popular languages, and I want to have a general model. But the cool thing is, if I work via this flow, every time I do an iteration, harder instances get into this labeled data set. The machine learning model will get better, but also the matcher. Because I'm labeling manually, I can also get inspired to add a new rule to the matcher. So every time I'm doing this, the matcher gets better, the machine learning model gets better, which also means that these moments where I disagree become more interesting. And I think this is a really nice way to think about solving a problem. It's also about understanding your problem a bit better. And to be honest, you could not have gotten here without this rule-based system. It actually helped me design all of this. And in the aftermath, one thing that I was happy with is, yes, the scores after became a lot worse than what I had before, but I didn't care because the data set that I'm applying this on is one that's more reliable. In particular, the main thing that I really loved seeing was the fact that the recall actually increased. So the precision stayed the same between both models, but now at least I had evidence that the machine learning model was generalizing beyond the rules that I had. And another thing that I really like is I have a rule-based system as well as a machine learning one. They both work on fundamentally different ways. So whenever they agree, I have a really strong signal that it's probably a programming language. So just a few observations. We've seen that a rule-based system definitely can save ML in situations where you don't have a lot of data. The rule-based system made the statistical system better. The statistical system also made the rule-based system better. The interaction wasn't just between systems. I, the human in the loop, also understood the failure scenarios of both models a lot better by doing this. And my labeling strategy is really effective now. But moreover, by thinking about rules this way and checking if they work, I have a fundamentally different way of approaching a machine learning problem. I'm actually iterating on my data here as well, and not just my model. And that is a fresh perspective if I compare it to what most people do when they call fit predict. So I hope that this demonstrates some of the utility of these rule-based systems, but it's not just with Spacey that I've noticed that this is super useful. I nowadays work for a conversational company, and what we do is we try to make a system that makes it easy for you to generate a very proper and very safe conversational agent, chatbots and that sort of stuff. And one thing that can happen when you're making such a system is that you can have a conversation in which the user asks the virtual assistant, "Are you a human?" And what we would like the virtual assistant to do primarily is to reply by saying, "Nope, I'm not a human. We really don't want to have the ethical concern that our systems are going to pretend to be humans." And after that, we really like them to recover the conversation that they were doing already. So at Rasa, when I just started, we had recently made the system that was really good at recovering. So it's actually quite hard to fool. I've tried it a bunch of times. But we now have a system that can take this training data, and it's really, really good at saying, well, okay, this is an interruption. We now have to get back to the topic at hand. But if you think about what's more important is this part, that no matter what happens in my conversation, I'm always able to say, I'm not a human. That's the ethical thing. That's the part that we actually care more of. And that's also where maybe there's a small concern. If you think about like an example of this, like the training data you would have for such a system, one risk that you might have is that all of these "are you a human" questions, that they're asked at the beginning of your conversation as opposed at the end. It can be that we have too many examples in our training data where we have easy examples, so to say, but that in production, if someone were to say at the end of a conversation, "Are you a human?" that we might not give this response, which is like super important. So then you can wonder, do we really want to have this decision being determined by a machine learning model? Or do we maybe just want to add a rule as an insurance policy? If we detect someone is asking this question, no matter what else is happening in the conversation, we must always reply that we're not a human. And if you think about it, that's also a rule-based system. And that idea of being able to add this insurance policy, that's actually a new feature that we've added in Rasa 2.0. It's something that is going to come out in a couple of weeks. Another way of fixing this issue is not to say, well, you have to introduce a rule. Certainly what you can also do is you can iterate on data. But one thing that's likely not going to help you is iterating on the model. It's going to be kind of dangerous if you really strictly care about this insurance policy to trust that the grid search will solve all of this. And that's kind of what we saw before as well. We kind of want to have systems that play by the rules. We don't just want to have an optimal grid search. We want to have models that have other types of properties that we're interested in. And at the moment, we might be overfitting on grid searches. So I've talked about the text use case now. Rules can save the day in data poor situations. Even without data, rules are awesome. Domain knowledge is great. We have safety mechanisms, and we can apply these rules to subsets of data that are really well understood. But the main question that you might have now for yourself is, can we do this on non-text data? Like, all of these results are great, but so far I've only argued for them in the text domain. And we can ask ourselves, well, can we maybe do this for tabular data as well? And I would say, yeah, I think we can. Let's say that you're World of Warcraft and you have session logs of every player that's ever played your video game. and you want to figure out who's going to churn and who's going to keep on playing. Sure, you can make a machine learning model. I think that's a good idea. But before you apply the machine learning model, there's probably also a rule you can just apply. If you're the kind of person that plays World of Warcraft at midnight during New Year's Eve, then you're probably a hardcore gamer. You're definitely well invested in this. Do we really need a machine learning model to tell us that you're probably not going to churn? Or can we maybe design a system where we say, well, you know what? We have some sort of a rule that just says you're a heavy user or you're not. And if you're a heavy user, then don't even bother with a machine learning algorithm. We kind of already know what's going to happen. Only when we have to resort to a machine learning model, that's when we're going to fall back to it. And there's actually lots of systems that can be written this way. Let's say you're doing fraud. I don't know, if you're a tax agency, if you're a child and you have above median income, okay, that's a risk. If you're a person with more than 10 bank accounts, I don't need a machine learning model, just you're a risk. That's already a business rule that I can go ahead and apply. Only after you've done lots of these rules, maybe then you can say, okay, and this is something I'm going to give to the machine learning model as a final resort, so to say. And you can even think of like proper safety constraints on the system. If you get a new data point X, and that data point X is considered an outlier, as in the machine learning model has never seen anything like it, then it shouldn't have an opinion on it. Maybe if we detect an outlier, we can also say, business rule, you got to fall back now. And if the certainty isn't high enough for your machine learning model, okay, another good reason to not automate the prediction. Again, we're dealing here with a rule-based system, and I hope that you would agree that you don't have to be in the text domain to take these rules kind of serious. There's actually something cool you can do if you can join your machine learning approach with these rules. Then the question is, though, I hope I've convinced you that at least in your mind you can agree that there has to be some interaction here. There's benefits to be had. It's not just benchmarking this system against machine learning. Interaction here will be cool. So now the only question you might have is, well, what can we do to make this as easy as possible to sort of use your human knowledge and rules in scikit-learn? And for that, I am announcing now that I have made this new package called Human Learn. And as the name might imply, you can kind of guess what it does. And what I'm going to do now is just give you a simple overview of two of the main features. It's my mom texting me. So here we go. I'm in a notebook, and let's say I've got this data set called Load Titanic. I have to predict whether or not you survived the Titanic disaster, and I'm able to do that based on all of this information. If I can come up with a simple rule, then one thing I can imagine is if you paid more for a ticket, you're probably closer to a lifeboat. I can definitely imagine that if you were a first class paid a lot, that you're more on the upper deck and probably not on the lower deck. So just as a benchmark, how about I just say, look, just take this column, the fare, and let's just pick a threshold. And if you're over the threshold, then you probably survived. And if you're under the threshold, you probably didn't. It's a simple machine learning model, but if only as a benchmark, I hope you would agree, it's not the worst idea. And what's the easiest way to write such a rule-based system in Python? Well, probably a function. What you're probably going to do is you're going to have a function that takes a data frame as input, maybe it has a threshold over here. And what you want to do then is you want to maybe say something like, hey, if we're over a certain threshold, predict 1, otherwise predict 0, and do that for all the rows. The only issue is that this function is not a scikit-learn compatible classifier. So the first thing that this library does is it just makes it easy to turn these functions into scikit-learn compatible classifiers. If you define it this way, you have your argument here that you also define here, then what this class will do is it will make sure that you have a function that you can grid search over, which in turn means you can use it for benchmarking. In particular, what you're going to see here below is the code that is needed to do that. But the more important and I think more interesting thing is that you can look at your grid search results and then see that, yeah, when you tweak your threshold parameter here, then you can see that just this one basic rule, it kind of already is able to achieve 60%-ish accuracy and an 80% precision. And just by making this rule-based system, there's also this notion that you're going to understand your data just a bit better. And it's not just this moment where you can make a classifier to make something that's accurate. What you can also do is make systems like this. You can also make systems that take pre-existing machine learning tools and turn those into a rule-based system as well. There's a bit of an example that I'll quickly just show you here. The most important thing to take away from this is that we have an outlier and a classifier model. And effectively what's happening inside of this function is we're saying this np-where clause a couple of times, where if this predicate holds, then we are going to override the prediction that we start with. So if nothing happens, we just go for the classification that we had. But if the probability is not high enough, then we have this fallback scenario. Otherwise, we have another fallback scenario. And lo and behold, you now have a system that can do the won't predict thing just by using tools that are available already. So we have these function tools. They are available as a classifier or regressor and as well as an outlier detector. But there's one other thing that I think is going to be a more interesting direction for this project. Because maybe we can not only think of how do we make rule-based systems easier, but also how can we make it easier to come up with rule-based systems in the first place? And the best way to summarize that, actually, is just to look at this chart. This is like the iris data set. This is just some sort of chart that you can look at. And I think the reason why a lot of us resort to machine learning probably has to do with the fact that it's kind of hard to automatically, come up with code that can sort of draw a shape around a data set, if you will. It'd be kind of nice if instead of, it'd be nice if we can just put an if statement down here and we'd have this shape. But unfortunately, code is not the right way to get there. But one thing that we can do is we maybe draw a classifier. Because to be honest, the way that this works, we've got these point and poly algorithms, right? So I can make a drawing of polygons of interest, and I can say, well, some of these polygons have a name attached that coincidentally is attached to the name of a class. And with these drawn polygons, I can also come up with nice little rules. And like the obvious rule could be, well, if a data point falls into a polygon, that's an excellent reason to say, oh, it probably belongs to a class. Another thing that I can do is I can maybe not just make one of these drawings, I can probably make many, and then I can average between the polygons that you fall into. Another thing that I can kind of do is I can say, well, if you don't fall in any polygons, you're probably an outlier. But I think the more important thing that's interesting about this is that by making models this way, not only do you have maybe a good benchmark for a model, but you're also doing your exploratory analysis at the same time. I kind of started getting a little bit tired of all of these people just calling fit predict XY and then calling it a day. If you look at Kaggle, there's a lot of that stuff happening, and it actually kind of gets scary. We shouldn't have that much faith in our machine learning systems. Instead, I think it's going to be a lot nicer to just draw models like this, see it as a benchmark, and if this model already kind of works, that's kind of nice, because it also means that we can maybe make these drawings for situations where labels are not available. We can also make these drawings for those situations, and we can also get domain knowledge in, again, if only as a benchmark. A final thing to maybe mention, just because I think it's a really cool feature, right, let's just also show that we can turn that drawing we just made into a classifier, by the way. So we get the 3 classes based on the drawings that we just made. But another thing that I think is just kind of nice to just sort of show you is that we can also give this chart not the labels, but just features that we're interested in. So let's say that I'm just kind of interested in, this subset of the data. What these charts also allow you to do is pass that information on to pandas. So if you're interested in a subset for research, you can also use this tool just for interactive exploration as well. So that was the brief demo. You might have a question. So one question could be, should I use it? Well, you're definitely free to. It's pip installable, documentation's ready, and there's also lots of tutorials. You might ask yourself, should I put it in production? I mean, it's a month old, maybe not. Open source works when folks contribute, when people contribute to find all the edge cases. And currently the edge cases are kind of unknown. Definitely feel free to collaborate, but don't put it in production just yet. Is it perfect? Nope, totally not. There's actually an extra risk of data leakage. Definitely watch out for that. It's super dangerous. And you also need to think about what you're doing because you can also add bad rules. And then you might ask, well, Vincent, why did you make this? Well, I'm getting tired. I'm looking at these machine learning models that don't play by the rules, and I think that that's actually a nice analogy of how we should think about our systems. We need these systems to play by the rules, Data professionals need to iterate on data and also keep thinking. And all this stuff needs to be easier. So this is my sort of answer to how maybe we should do this. Then you might ask, Vincent, what's your best feature in this entire package? Which is why I asked people like, hey, shall I end with a poem? Koen, I will not be doing it in Brabants, unfortunately, because I think the minority of the people watching understand that. But the best feature of the entire package is what you can do is from ulearn, you can call import this. And it shows you all the lessons that I've learned while making this package in rhyme. Why worry about the state of the art? Maybe it's time that we all admit that one size-fits-all suit is not bespoke and usually does not fit. Computers can flow a lot of tensors, but they never really learn. Natural intelligence is still a good idea, and natural stupidity is a valid concern. There are many ways to solve a problem, but don't let fancy tools get to your head. Why would you choose a predefined solution if you can create a custom one instead? Thanks everyone for listening. If you're interested, I will be making more spacey content. Keep an eye on Twitter. I will definitely have like a big announcement about that one of these days. If you're interested in this human learn thing, I've added a free course on Calm Code.io. It has like a full tutorial, so you can totally go around and check that. If you're interested in NLP though, also just reach out to me. I'm doing a bunch of open source work in NLP space. And there's also a YouTube channel where I explain algorithms if that's of interest. Thanks for listening.
Thank you, Vincent. Actually, we have quite some interesting questions. So,
oh, wait, I want to answer one question first, because the previous speaker was talking about missing data, right?
Okay.
Let's do that thing first. Another way of dealing with missing data, by the way, if you make a model that's like this drawing, notice that if a data point is missing on these two columns, right, but it's not missing on these two, you can still say, oh, but it falls in this polygon, so I can still make a prediction. Just saying, it's another way of thinking about dealing with missing data. You can also ignore it. Anyway, questions, I guess?
Yes, a question from Jorn. Why would embeddings not be suitable? Wouldn't they be able to encode the context in which the programming language tokens appear in sentences about the beginning of your talk?
Oh, well, if you're going to end up training your own, maybe, but certainly not the pre-trained ones, right? That's the main thing. The pre-trained ones that are trained on Wikipedia probably will overfit on the general case and not directly applicable to what I'm using. That's the thing. Like in general, the word go is really reserved to be a verb. Like there's no way around that. It's really the most common usage for it. Even in a Stack Overflow dataset, there's more use cases for go being a verb than it for being a programming language, even in this use case. So training your own embeddings, you can try, but it's not easy.
Okay, then on to the next question from Ekter. Business process management and integration of machine learning system inside workflow makes good sense, but does this mean we take data away from machine learning model during training phase? Or should we train with full data, but only serve the model for the ones that fall out of the business domain rules?
That's a lot of business terms. So in this particular case, if you're going to do the drawing approach, and even if you do the function classifier approach, there's not really fitting anymore, is it? You're just saying, well, I as a human declare that these are the rules to follow, and those are the rules you should just take into consideration. I forgot about the first part of the question now, sorry.
Yeah, basically it's, should we train a machine learning model on the complete data set or only on the data that has been filtered by the business rules?
I don't have a good answer for that in general. Just try it out on your own data. That's I think the best way to verify it for sure. Again, the risk here is that you can also come up with rules that make no sense and are actually bad, right? So that's the new hypothesis you will have to concern yourself with.
Okay, cool. And then a question from Juan, which is quite interesting, I think. So the iterative method that you propose, would you consider it to be some kind of active learning that you apply?
I mean, that's one way of thinking. I mean, I'm not super aware of the exact definition of active learning. I'm just copying what the Spacey people call it, which I think Ines was the first one to coin iterate on your data instead. And the reason why I sympathize with it is also that you have to be careful because a lot of these labeled data sets can't really be trusted. So that's more the concern that I have. I have more the concern that there might be a labeling issue, I suppose, than that I'm trying to not label as much. I think active learning as a field is a little bit more concerned with, well, labeling is expensive. How can we minimize the costs? Whereas my concern is a little bit more, well, do I even trust the data to begin with?
Yeah. I think so. Basically, what you're saying is that if you take a out-of-the-box active learning approach, probably it's not really covering it, because then you're still using a model to see where you're inaccurate, while your business rules actually have a more human training approach, right?
The main reason why I think this approach works is because the rule-based systems indeed work on a very different method than the machine learning one. With active learning, as you just said, I do think it's a valid concern that if there's bias in your data set in the first place, that active learning is maybe gonna keep it.
And so you're basically using the human intelligence to find your edge cases that you're missing if you just look at your accuracy, right?
Yeah, and I think natural intelligence is still a pretty good idea. I mean, artificial intelligence can work, but human intelligence sounds good.
So then there's another question about the Snorkel project. You're familiar with that project?
A little bit. I've talked to people who use it. So I know people who use it in fraud situations. And one story I heard is that someone's actually quite happy with it. I don't know it well enough to understand the magic that it does under the hood. I believe it basically says, well, you got a couple of rules that we don't fully trust, and then we combine them in a magic way, and then it's better. It's just that I don't understand what the magic way exactly entails in order for me to give confidence in it.
Yeah. It really sounds like magic, right?
Yeah, so there's
a little bit of a black box thing to it also.
Yeah, and again, I wouldn't want to suggest that rule-based systems are the end-all of everything. Like it's more of a tool that you can use, and I think it's started getting a bad reputation, even though I keep seeing it does wonders. So that's why I figured maybe just talking about it.
Let's see what we have. Actually, a lot of questions. Yeah, so I think we're running late already a little bit. So let's move the questions to Discord, and we can continue the discussion there.
Sure thing.
Meanwhile, a little bit of an announcement. We have one talk that is unfortunately cancelled. So that's the talk about the second one after the break from Sri. Yeah, so we have some last minute schedule changes. So just a heads up that this talk unfortunately will be cancelled. So it's the one about the reinforcement learning in greenhouses. So Vincent, thank you very much for your talk. Yeah, let's continue the discussion on Discord.
I will I will definitely respond to anyone, anytime. Thanks.
Yes, I know. Thank you, Vincent.
Ciao, thanks.